In this problem, we're asked, what is the probability of getting 2 pairs in a game of 5-card poker? All right. So in this game, we have 5 cards in our hand, and we want to know what is the probability of this being a pair, this being a pair, and this being some 5th card. Okay, and the remaining card here can't be the same card as one of the cards in either of our pairs, right? Because otherwise we'd have a pair and a 3 of a kind. And there are actually many ways to calculate this probability, and I'll go through each of them very quickly here. So this is pretty much the standard solution that you'll see when you're taught how to calculate the probabilities of 5-card poker. So you have essentially 52 cards in a deck, and you have 4 suits. You have spades, clubs, diamonds, and hearts. And then in each of those 4 suits, you have 13 cards. So you have an ace, you have a 2, 3, 4, 5, 6, 7, 8, 9, 10, and then you have a jack, a queen, and a king. All right, so let's figure out what we would need to draw for the 2 pairs. Now keep in mind, we're going to be using combination because the order doesn't matter. It actually doesn't matter how we draw this card versus that card, but it also doesn't matter that we draw this card, then this card, then this card, then this card. Or perhaps we draw out of the deck this pair and then this pair, or this pair and then that pair. So we need to keep this in mind. So the first thing that we'll do is, out of 13 cards, we're choosing 2 unique values. So we have 13 choose 2. Right? So this could be a 6 and a queen, for example, or it could be a 7 and a king, or an ace and a 2, or something like this. And then for each of these pairs that we're drawing, we need to pull at least 2 suits out of the 4. We could pull a spade and a diamond, or a heart and a club, or something like this for the first pair. So that's for 4 choose 2. And then we need 2 suits for the second pair, and that again is 4 choose 2. And finally, for the 5th card that remains, we need to choose out of the 11 cards that remain 1 card, right? So if we've picked a 6 and a queen, we have to pick something other than 6 or queen. We could pick a jack, a king, a 10, a 9, an 8, 7, 5, 4, 3, 2, or an ace. And then of that card that we pick, that particular card type, we need a particular denomination. And it really doesn't matter, in this case, the suit doesn't really matter. So out of 4 suits to choose from, we just need to choose 1. And this would essentially give us 123,552 possible ways in which the order does not matter that we could pick these 5 cards. Now, or we could do it this way. We could say 13 choose 2 times 4 choose 2 times 4 choose 2, and then we could realize that this 5th card must be selected out of the 44 cards that remain. Now keep in mind, we've picked 2 cards for the first pair plus 2 for the second pair, but then there are still 2 6s and 2 queens left in the deck, so we can't pick those either. So that equals 8 cards that we can't pick for the 5th card. And so 52 possible cards minus 8 gives us 44. So this could be rewritten as 44 choose 1. And we would get the same number of combinations here. Now there's also another way that we could do this. Another way we could do this, we could try to do it, or try to make sense of this using each pair at a time. Say you were tempted to take 13 choose 1 for the first card, multiplied by 4 choose 2 to pick the 2 suits, and then you multiplied that times 12 choose 1 times 4 choose 2. Let's ignore the 5th card there. I guess we could also multiply this by 44 choose 1. The problem with this method is that we've accidentally included the order in this. In other words, we've essentially said that we could choose a king then a queen, or a queen then a king. And we've included both of those options in here, even though we actually really don't care about the order. In other words, we've somehow turned this into a permutation. And you'll notice the difference here is that in the first case we used 13 choose 2, and in this second case we used 13 choose 1 times 12 choose 1. And what's the difference here? In this first case, we'll have 13 times 12 divided by 2. And this essentially tells us there's 2 ways for us to pick the first pair and then the second pair. And in this case, we just have 13 times 12. In other words, we've included twice as many ways that we could draw this because we've included the permutations or the order in which we're drawing them. But the order doesn't matter. And these don't equal each other. In order for them to equal each other, we would have to multiply this second option by 1/2 or divide by a factor of 2. And so if you want to do it in this third possible way, we'd say this is 13 choose 1 times 4 choose 2 times 12 choose 1 times 4 choose 2, right? This is the first pair, the second pair, first pair, second pair, and then we'd multiply this by 1/2 so as to account, so as not to overcount the number of ways that we could do this, times 44 choose 1, and again we would be left with 123,552, which is correct. So this still doesn't tell us the overall probability, though. The probability, as you may recall from earlier chapters, is the probability of some event, let's say of getting 2 pairs, right? We'll call that event A, divided by the total possible ways that we could do this, right? Total probability. And what is the total probability? Well, the total probability is just 52 choose 5, right? Because we're just picking 5 cards out of 52, and again, the order doesn't matter. This is equal to 2,598,960. So all in all, our total probability, our probability of getting 2 pairs in 5-card poker is equal to 123,552 divided by the total probability, 2,598,960, and this yields a result of 0.0475. In other words, a 4.75% probability of getting 2 pairs in a game of 5-card poker.